4 hazards. 1 constrained edge computer. What happens when wildfire detection, seismic monitoring, flood sensing, and landslide analysis all need compute at the same time? That is the problem I built Sentinel Edge to solve. Sentinel Edge is an offline-first physical AI platform that runs 4 hazard monitoring workloads together and dynamically decides what should run now, what can wait, and what must never be starved. At the center is the Arm AI orchestrator. For this hackathon, I validate the system in a reproducible Arm64 environment, using Arm64-emulated Runtime where applicable. The camera, IMU, rainfall, water level, soil moisture, tilt, and vibration streams are deterministic simulations, but they enter through the same acquisition contracts designed for physical sensors. Wildfire monitoring uses simulated camera input, smoke persistence, ambiguity handling, and wakes heavier inference only when needed. Earthquake monitoring processes a continuous 3-axis IMU stream and gets a reserved high-priority path. Flood monitoring tracks rainfall, water level, and rate of rise. And landslide monitoring combines rainfall, soil conditions, tilt, and vibration. But the interesting part happens when they all compete for resources. Here I trigger the deterministic multi-hazard scenario. Smoke appears. Rainfall increases. Water begins rising. Slope conditions deteriorate. And then an earthquake-like signal arrives. Watch the scheduler. The seismic workload receives its reserved tier A capacity, while lower priority work is deferred instead of blocking it. Wildfire heavy inference wakes when required, environmental monitoring adapts its cadence, and queues remain bounded. If the system cannot maintain its guarantees, it reports overload instead of pretending everything is fine. These are not UI shortcuts. Simulated observations travel through the normal processing pipeline, and the incident and event engine remains the sole authority for incident state. Each incident keeps its timeline, evidence, provenance, uncertainty, and monitoring context. AI-assisted investigation can help explain what happened and recommend next steps, while deterministic application logic remains in control of authoritative state. And because this is an AI optimization challenge, I wanted the optimization story to be measurable. I compare 3 configurations. B0 is the naive fixed-rate baseline. B1 adds optimized model and runtime behavior while keeping the same fixed-rate workload. And O1 adds the orchestrator, adaptive cadence, workload admission, wildfire wake and sleep behavior, and seismic reservation. All 3 use the same deterministic workload and quality guardrails, so I can separate runtime optimization from orchestration itself. The core demo requires no cloud account, no API key, no live data source, and no physical sensor. It is designed to be reproducible, inspectable, and useful even when connectivity disappears. Sentinel Edge is my experiment in making physical AI smarter about something individual models usually ignore: limited compute. Run the right workload, at the right time, for the right reason. That is Sentinel Edge.